Now, there's a bunch of different techniques for dividing. Long division was a very common one, and to review how long division would work is that when you were asked to divide 2,748 by 13, they said start looking at your biggest numbers. Well, there's no 13s in 2, but if I go to 27, how many 13s fit in 27? And the answer is 2, and you would write the 2 above the 7, and then you would say, okay, I'll multiply 2 times 13 and get 26, because that's how close I was to 27. Now, what you probably or maybe didn't understand in middle school is that by putting that 2 right above the 7, you're really putting that 2 in a hundreds column. That 2 really represents 200. And when you're asking how many 13s in 27, this is really 27 hundredths. That's what those first two 27s. So when I do 2 times 13 and get 26, you often didn't write these down, but for understanding, you're really saying, I want 200. 200 13s makes 2600. And if I subtract, I would still be left with 148. Then we repeat this process, and now you switch colors. Now, if I look from left to right, I get 14. How many 13s in 14? 1. And I put that 1 over my tens column because really that represents 10. 1 times 13 is 13. Technically, there could be a 0 there if you think of it as a 10. And then when I subtract, I get 18. Well, how many 13s are there in 18? I could switch colors again. And I said, well, there's 1 13 in 18. If I subtract, I get 5. And that would be a remainder of 5. So long division, it was a technique to systematically go through and get the answer. Since then, there's been other techniques, but the long division is going to work really nice for us when we do algebra. Sometimes I've seen people, they start with 2,748 on this side, and then they just start counting 13s. Let's say, I'll do 100 of them. Well, that would be 1,300, right? If you subtracted, now you're left with 1,448. I could do another 100 of them. And if you take away another 1,300, and that would leave you with 148. And in this method, it didn't matter that I had to get the 200 first. Long division, you have to get the right number to keep going. But in this method, you'd be like, oh, I just want to take, you could go really slow. I'll do 1. All right, subtract that, I'm left with 135. Ooh, I'll do another one. Like, we could go on forever doing 1 at a time. Eventually, you're going to add them all up and get 211, and the last number that's left on the left-hand side will be a 5. So this is another technique. What's really nice about this technique is you're not set to get the right answer every single time. What you need?
I was just looking for some, do you have some?
Right in that top drawer, there should be some. But the long division, you have to get the right number first. The 26. So here in the second example, again, in 42. How many 27s are in 42? 1. And when I subtract, I still get 1, 5, 1, 2. Because technically that 1 is 100, you could put 2 zeros there to think that you're subtracting 2,700. Now, switch colors. There's no 27s in 15. I have to go all the way to 151. A little bit of mental math here. How many 27s in 151? Can we fit 5? 6 would be too much, right? 5 of them would be 135. Again, I subtract, and this will leave me with 162. Because technically that 5 is a 50. You could add a 0 on the end there. And then that works out nicely. Oh, switch colors again. 6 times 27 is perfectly 162. So we get a remainder of 0, and this means it divides perfectly. Okay? Mathematically, we can say a few things about both of these answers. Scroll down just a little bit. Mathematically, the first one, if we do 2,748 and divide it by 13, and we get 211, that is telling us that 2,748 is equal to 13 times 211. But it's not quite perfect, right? There was a remainder of 5. If you multiply this out, you would get 2,743. Adding the 5 would make it equal perfectly. We could also divide everything by 13 and write this statement as 2,748 divided by 13 is equal to 211. But then there's a remainder of 5 that still needs to get divided by 13. That 5 that was left, and maybe you learned in middle school how to put a decimal place and do zeros afterwards, and you could keep on going for a very long time. The second one, we could say that 4,212 is equal to 27 times by 156, and there's no remainder, so we have actually divided this one perfectly. We found the factors of it perfectly that way by showing that there was no remainder. So we're going to use this idea of long division in algebra. And we're going to look at the construct the understanding and see how that would look. So the first one, we're going to take 3x squared minus 4x plus 5 divided by x minus 2. And we're going to use a very similar idea that we did for long division with numbers. In long division with numbers, we started from the left-hand side and we looked at a number. And we said, can we get close to that? We do the same thing in algebra. We say, is there something I could multiply x minus 2 to get a 3x squared? In particular, the 2 doesn't really matter. Is there something you could multiply the x by to get a 3x squared? You would have to multiply that x by a 3x. And just like we write things in columns with numbers, the 3x should go over the column of the x's. And if I multiply 3x times x, sure enough, I get 3x squared. And if I multiply the 3x times the minus 2, you're like, ooh, we were close but not perfect, right? We get a minus 6x. Scrolling up, what did you do with whatever number you got in long division? What was our next step? How did I get the 148? I subtracted. The same thing's going to happen here, but you've got to be careful because you're subtracting all of this. So it might make sense to put brackets, put a subtract sign, and what beautifully happens is the 3x squared minus 3x squared goes away completely. The minus 4x minus a negative 6x is going to be plus 2x, and 5 minus nothing, you still have plus 5. And just like in the long division, I'm going to switch colors. I'm going to go to blue. Now, my first number is a 2x. Is there something you could multiply the x by to get a 2x? Yes, it would be a plus 2. So we write plus 2. And 2 times the x would be 2x. And 2 times the negative 2 would be negative 4. Put it in brackets. Put a subtract sign on in front. The 2x minus 2x nicely goes away. And 5 minus a negative 4 gives us 9. We have a remainder of 9. mathematically, what does this mean? Right? This means that if 3x squared minus 4x plus 5, 3x squared minus 4x plus 5 is equal to, when I divide it by x minus 2, I get 3x plus 2. And that's very close to being perfect. In fact, if you multiply that out in your head, you're going to get 3x squared. Your outside and your inside give you minus 4x. But unfortunately, the last terms don't give us 5. They give us minus 4. We had a remainder of 9. You'd have to add 9 to this to make it work. Ooh, something exciting is going to happen in this one. Process stays the same. And I'll keep, when I switched from green to blue, do you see I just did the same thing again with my new numbers? That's how long division works. You have a process that you just keep repeating until you can't do it anymore. And once I got to the 9, there's nothing you can multiply the x by to get a 9 without going into fractions, and we don't go into fractions. So, I look at my 2x cubed. Is there something I can multiply x by to get 2x cubed? 2x squared. And if I multiply 2x squared times x, for sure, I get my 2x cubed. And my 2x squared times my plus 1 would give me plus 2x squared. Put it in brackets and subtract. The 2x cubes go away completely, and a minus x squared minus a 2 gives me minus 3x squared. And then all of these don't have anything to subtract, so they would just still be there. Next, now, my leading term is a minus 3x squared. I do the same process. I say, is there something I can multiply my x by to get a minus 3x squared? Well, yes, there is. That would be minus 3x. So minus 3x times the x, for sure, that gives me minus 3x squared. And minus 3x times the plus 1 gives me minus 3x. So we distribute and subtract. This goes away perfectly. Negative 2x minus a negative is adding. That'll be x. And then plus 1. Switch colors. Now my leading term is an x. Is there something you can multiply the x by to get x? 1. Plus 1. And 1 times x is x. And 1 times 1 is plus 1. Put it in brackets and subtract. And beautifully, we have no remainder. Now, what does this mean? This is where things get exciting. We had, oops, can't see it anymore. We had 2x cubed minus x squared minus 2x plus 1 is divided. We divided by x plus 1, and we got 2x squared minus 3x plus 1 as an answer without a remainder. And for many of you, this is the first time in your life that you have factored a cubic equation. You can factor x squared equations pretty good. But if I asked you, can you factor 2x cubed minus x squared minus 2x plus 1? The answer would probably be no. But we just started it. In fact, we could keep going. This x plus 1, this factors nicely. 2x and x, 1 and 1, minus and minus. And now we have factored this completely. So what we're going to find is that this unit is leading us up to be able to factor things beyond x squareds. You're able to factor x squareds in the past, but it only factors if we got a remainder of 0. So we'll go to example 1. And just like many things in math, if we want to do long division, we have to set it up correctly. 1, there are 2 rules for setting things up. We have to write our terms in descending order by degree. And when we talk about degree, you can put in brackets here. Something with an exponent of 3, we say has a degree of 3. Something with an exponent of 2 has a degree of 2. Can you see our example isn't in the right order? And when you factored x squared ones, don't you always put the x squared first, then the x, then the number? You are used to putting things in descending order by degree, and we need to do that for long division as well. Second main setup thing. If a term is missing, like if you have an x cubed one, but there's no x squareds in the question, we'll actually write 0x squared for that. That's going to come up in the second example, not our first example here. So these 2 things are a setup. Group them together. And I can make it smaller off to the side because you've got it written down already. So I go to set up my long division, x minus 1, I draw the big thing, but the order is important. The biggest degree that I have is 3. And then I have a plus 3x squared, I'd write that second. Minus 2x would get written third, and a plus 5 would get written last. This is our set. See if in your head you can keep 1 step ahead of me. All right? So our first term, the 2x cubed. What could I multiply the x by to get the 2x cubed? A 2x squared. And I multiply that 2x squared by both the x, which gives me the 2x cubed, and by the minus 1, minus 2x squared. Put it in brackets and subtract. Between minus and negative 5. Number 1 mistake that happens in long division is working with integers. So be careful when you're adding negatives, subtracting negatives. Take your time. Switch colors here. My new first number is a 5x squared. Is there something I can multiply x by to get 5x squared? Well, it would be a positive 5x. And 5x times x, for sure, gives me the 5x squared. And 5x times the minus 1 gives me minus 5x. Put it in brackets and subtract. Negative 2 minus a negative, this will be plus 3x. Plus 5. Switch colors, now I have a 3x as my first term. Is there something you can multiply x by to get a 3x? Plus 3. 3x times x is 3x. 3x times a negative 1 is minus 3. Put it in brackets and subtract. 5 minus a negative 3 is 8. And that is our remainder. Okay? And we can write our answer then. And one thing that we're going to highlight it on the next page. So maybe I'll include it as part of this note. Maybe we'll highlight it first, and then we'll come back to this question and talk about it. So on the next page, they talk about the division statement, and right above the division statement, we're going to write the following to help us remember it. They have polynomial, what you were dividing by, what your answer is, plus the remainder. I like to write it like this. Your polynomial is equal to whatever you were dividing by is your divisor, which we'll use the letter D. Whatever your answer is Q for quotient, because the answer to a dividing thing is a quotient. And then plus remainder. And I think it's easy to remember if you like ice cream, because it's got like DQ built into it. So it should make you a little bit happy if you like ice cream. And we can take any answer that we got from our long division and write the division statement. And we were doing this with our long division already. So if I go back to our example that we did, okay? The division statement would look like this. We had 2x cubed plus 3x squared minus 2x plus 5. This was our polynomial. It's equal to, what did we divide by? We divided by x minus 1. This was our divisor. What did we get as an answer? We got 2x squared plus 5x plus 3. This is our quotient. And then did we have a remainder? Yes. Our remainder is 8. So what we're saying here with something that gets a remainder is that x minus 1 times 2x squared plus 5x plus 3 is as close as you can get to this polynomial. If you actually distribute this, you will get the 2x cubed. You will get a 3x squared. You will get a minus 2x, but unfortunately the minus 1 times 3, the last one will end up being minus 3. Everything worked except for the last number. And so we have a remainder that we'd have to add to make it work. Ultimately, we're going to be looking for ones so we can factor that have no remainder. But for right now, this one did have a remainder. Okay, questions for practice? 3A, C, and D, and 5.